All right, it's about time to wrap up this big topic on feature selection. So in this video, I will show you how we can use sequential feature selection in Python. And I will start by showing you an example in mlxtend. That's the original implementation that I created many years ago. And then later on, I will also show you how we can do the same thing in scikit-learn using, let's say, streamlined implementation with fewer bells and whistles. So also I encourage you to check out the documentation here, which contains a lot of more additional examples, which I will not be covering in this video. Because I don't want to make this video too long and too bloated. So let's get started by loading Watermark, which is a plugin I developed many years ago to just track the versions of my notebooks. Because software libraries update over the years, and it's always good to make sure that the version numbers match what we expect. Just in case, let's say, some options don't work anymore, this would be a good place to make sure that you have similar version numbers when you're running this notebook. Of course, newer version numbers are always a good idea too, but if in case something doesn't work, might be related to, let's say, that you have a very different version number. We will also be using matplotlib later, so here I'm just importing matplotlib so that the plots will show in the notebook. So our first real step is preparing the dataset. So like before in the previous videos, we will be using the wine dataset. So here we are loading it from the UCI machine learning dataset repository using pandas. Then we have our labels for the column names of the dataset. And here I'm just printing out some basic information. So just checking that everything loaded okay. And also making sure that we have the class labels as integers. Okay, so then what we will do is we will divide the dataset into a training and a test set, and we will also standardize the dataset. That's because we will be working with a k-nearest neighbor classifier, and k-nearest neighbor classifiers, as we have learned in the very first lecture in this course, is sensitive to scaling. Okay, let's divide the data set here into training and test sets. So the test set is 20% of the data, and the training set is then correspondingly 80% of the data set. And here we also standardize the training and the test set. So nothing new at this point. This is something we have been doing all along in all the previous videos as well. Just to establish a baseline before we get to feature selection, let me fit a k-nearest neighbor classifier on the standardized dataset and then compute the training and the test accuracy. By the way, I should mention I'm just using arbitrarily 5 neighbors, but of course this would also be subject to grid search. And in fact, you can combine grid search and sequential feature selection. I'm not going to do this here just to keep the code and the video simpler, but there are many examples of that I added to the documentation I mentioned earlier. Okay, so looking at the baseline results now, what we see is we get 98.6% accuracy on the training set and 94% accuracy on the test set. So we can see the performance is pretty good using the 13 features in the wine data set, but we can also see that there is some overfitting. And like we discussed in the k-nearest neighbor lecture, k-nearest neighbors is one of these classifiers that is kind of like susceptible to the curse of dimensionality. So here it might make sense to select fewer features because that might help overcoming the curse of dimensionality and improving the performance here. So let's start by showing you how we can use sequential feature selection to select a couple of features. So here we will be using 5 features. Why 5 features? Also just an arbitrary choice. So later I will also show you how we can look at which is a good feature size subset. So whether it should be 4, 3, 2, 5, 6, 7 features and so forth. So that will be the topic of the next section. Here, let's just assume we care about a feature subset that consists of 5 features. So it's slightly less than half of the original number of features. It's more like 1/3 because originally we have 13 features and now we have 5 features. So we reduce the size of the feature set by approximately 2/3. So we start by importing the sequential feature selector from mlxtend feature selection. And just to save typing efforts, I will just import it as SFS to make it shorter. So this receives as input the model itself. Then we can decide how big our feature subset should be. And then we can select whether we want forward or backward selection. So if you set that to false, it will perform backward selection. And then there's also the option of performing floating forward or floating backward selection. So setting this to false will be resulting in a regular sequential forward selection. The verbose parameter is for showing output during training, and this can be particularly useful if you have, let's say, a very large data set and you are evaluating a lot of, let's say, iterations. So if you have a large data set and you select a small number of features, there will be a lot of iterations, and it might make sense to show some output so that you can approximately guess how long it will take to complete. You can also choose what scoring metric you want to use. So by default, it should use accuracy for classifiers and R² for regression models. But just to be explicit, we will be using accuracy here for the model evaluation for evaluating the feature subsets. There is also a CV option here. So CV stands for cross-validation. So here it will do 5-fold cross-validation to evaluate how good a particular feature subset is. So using cross-validation together with sequential feature selection is always a good idea to prevent also overfitting when selecting these feature subsets. There should also be an optional njobs parameter, which you can set to -1 to fit things in parallel. That is also good for improving the runtime performance. So let's fit this model. And you can see it's on my computer running 8 jobs in parallel to make things faster. You can also just set it to 1 or none. So if you don't want to use multiprocessing, but if your computer supports that, it's usually not a bad idea. So you can see some output here. By the way, if you don't want to see so much output, you just set that to 0 or to 1, then it will show you fewer output. But what we can see here is it's fitting things. And then in the end, so you can also see 1 out of 2, 2 out of 5, 1 out of 5, 2 out of 5, 3 out of 5, and 4 out of 5 features until it reaches the 5 out of 5 features. Because it's forward selection, it will start with 1 feature and stop with 5 features. And you can also see the performance of the different feature subsets. And you can see here that the performance improves the more features we use. So here we get 99% accuracy using 5-fold cross-validation. After this has finished, we can then look at the feature indices. So here we have indices 0, 6, 9, 10, and 12 as the selected features for our 5 feature subset. And if we are interested in the names, there are 2 ways to do that. So first, if I go back maybe for a second, we could be actually using a data frame directly in sequential feature selection, and then we can also directly access the column names. But some scikit-learn operations don't support that. Or for example, the standard scaler, if you would give it, let's say, a data frame, if you would do this, it will still result, either the standard scaler or the train test split function, it will still result in a NumPy array. So in that case, you would have to do certain steps here manually if you want to fit the SFS on a data frame. So in any case, it was like a little side note. So here, these are the indices of the features. And if you fit SFS on a data frame, you could also access the feature names directly using here k feature names _. Otherwise, we have the feature names in columns, right? So we could also just use this one here as a mask to select the feature names from our columns. So here, the best subset of features is alcohol, flavonoids, color intensity, hue, and proline. Okay, so now that we have selected these, the subset of 5 features, let's take a look at the model performance of a k-nearest neighbor model fit on this particular subset. So what we get here is 99% training accuracy. I believe that was also true previously when we fit the KNN model on the whole data set. But what we can see now is that the test accuracy has improved. Now we get here 97%. think before it was 94.44%. So yeah, the feature selection here was successful in terms of selecting a feature subset that improves the performance of the model. Yeah, so in this section now I want to show you some additional things we can take a look at after fitting the sequential feature selector. So after fitting the SFS object, we have this subsets._ attribute, which will give us a lot of information about our sequential feature selection run. So here, this is a dictionary that contains all the different feature subset sizes, so 1, 2, 3, 4, and 5. And for each feature subset, we have the cross-validation scores. So these should be the 5 cross-validation scores, and then this is the average score. If you use the pandas data frame, this one would also reflect the column name of the feature subsets, which is also sometimes useful if you, let's say, want to really more easily read what these features are instead of looking at these arbitrary indices. Now, this dictionary contains all the information that we might need, but it is not super pleasant to look at. So I will show you how we can show these results in a data frame more conveniently, but before doing that, we can also collect additional information. So I implemented this getMetricDict function, which will also, in addition to let's say just showing the cross-validation results, compute standard errors and the confidence interval. So if you carry out this optional step here, it will add more information to this dictionary. So there are the confidence interval bounds, the standard deviation, and the standard error of the cross-validation scores. Now, we can use this dictionary to show it more, let's say, pleasantly in a pandas data frame, which is what I'm doing here by calling pandas.dataframe from dictionary on our metric dictionary. So I think this is already much easier to look at than the dictionary above. So here again, you have the different feature subset sizes with the different indices of features. And then we can look at the average performance here in this column. And we also have the confidence interval and standard deviation and standard error and so forth. But yeah, sometimes it's even more convenient to look at this in terms of a plot. So there's also this plot sequential feature selection function in mlxtend.plotting, which I'm importing here. And here I'm now creating a plot with the standard deviation as the error bars. So looking at this, we have our plot now. And yeah, I think this is a really nice visualization where we have the accuracy on the y-axis and then the sizes of the different features or feature subsets on the x-axis. So we have one feature and we can see that the more features we add to our subset, the further it improves. Now, you may wonder, I mean, there is certainly a trend here. You may wonder if it might be beneficial to have even 6 or 7 features in our subset. So this is what we will be looking at in the next section. So where we will look at all possible subset sizes and then see which one gives us the best performance. Yeah, so in the previous section, we saw how we can use the SFS to select a feature subset of a very specific size. We chose the size to be 5, but it was relatively arbitrary. So in this section, I want to show you how we can be, let's say, more flexible with that. So for example, you might be interested in a feature subset between, let's say, size 3 and size 10. So you can actually, put in a tuple here as an argument. And then it will evaluate all subset sizes between 3 and 10 and give you the best performing one as a result. However, sometimes you are even, let's say, less constrained and you really just care about what is the best feature subset of any size using sequential forward selection. In this case, you can set the lower limit to 1 and the upper limit to the size of your data set. You can also basically more arbitrarily or more generally set the shape to 1. That is the size of or the number of features in your data set. Or even more conveniently, you can just set this to best and then it will select the best feature subset of any size. So let's run this here. And then after running this, so notice that there are no results because we set verbose to 0, so it's not printing anything. But yeah, we can see it has finished here. And then what we do is we again take a look at our plot. So here I'm first computing also the standard deviation and confidence interval and standard error. So just setting it to some value here. And then I'm plotting this metric dictionary using the plot SFS function again. So now here, what we can see is all the different feature subset sizes that were selected by sequential forward selection. So we can see here 1 to 5 is what we have seen before. So there's no change because we already evaluated that previously. There shouldn't be any difference. We have now these additional feature subsets from 6 to 13. And here you can see that the performance of the size of feature subset size of 5 is actually the best one here. So looking at this plot is actually very useful to determine what is a good feature subset size or what number of features should we use. And yeah, we can see here there's also more variability around using more features. So actually sometimes it might be good to focus also on a feature subset that has a low variability but gives us also the best performance. And here 5 seems like a good one. And since this is also the best performing one, it should be the one that is returned or that is saved here by the SFS. So when we do that, we get the subset of 5 features because it's the best performing one. And again, we can see these are the same ones that we actually got previously here too. Yeah, and then I think I skipped over this previously. Once we have the features, let me scroll up again. We can, of course, use the sequential feature selection object to perform this transform, which will then, of course, give us the subset of features we want to select based on these indices here. So there's a transform method after fitting that we can use to transform the training set and the test set. So this is all I wanted to say about the basic usage of the sequential feature selector. And yeah, again, like if you're interested, there is this link with more usage examples, including how we can use it in grid search and so forth. So I also want to show you how to do sequential feature selection in scikit-learn. But before doing that, a little side note here. Let's take a look at exhaustive search. So in the previous video, I mentioned that exhaustive search is the only method that guarantees us to find the optimal feature subset. Because sequential feature selection, after all, is still an approximation method. So in the previous video, I also showed you how we can compute the number of combinations for different feature subsets. So if we have the wine data set, we have 13 features. And if we select or consider all different subset sizes and do an exhaustive search, the number of combinations is 8,191, which is a large number, but I would say this is still doable or reasonable. I recommend in practice always computing this before running an exhaustive search, because if you have, let's say, something that is greater than 100,000 or 1 million, it might not be feasible to run this on your computer. Yeah, and to make this computation convenient, there is also a num combinations function in mlxtend, which you can import from mlxtend math. So here I'm computing now the sum of all the combinations. So each one will compute the combinations for a specific n. So the n here represents the m. Actually, I should have maybe used a more consistent notation. And k here represents this I here. So this is for, let's say, 13, selecting, let's say, one feature out of 13. And then I'm repeating this for all the different subset sizes, so from 1 to 13. And then, the sum is essentially the sum here. So here, this should give me a number like 8,191. Okay, so now we, let's say, think that this is still a reasonable number that shouldn't take too long because the wine data set is relatively small. I think it's below 1,000 training examples. So here we are using the exhaustive feature selector from mlxtend, and this one will allow us to specify a minimum number of features and a maximum number of features. So here we are looking at any feature set size between 1 and 13, where 13 is the maximum size in our data set. Maybe it's better to keep it more general, so we can reuse the code for different data sets. We can maybe write it like that. We are also printing the progress because it can sometimes be useful, especially if you have expensive model to train or you have a large data set, a lot of training examples. It might make sense sometimes to print the progress so you can see or guess or eyeball how long it might take to finish this run. So let's run this here. And it should not take too long. Let's maybe see. One problem, there we go. So one problem with Jupyter is that it is not super often updating the display here. But we selected now 8,191 features. Didn't take that long, so which was fine. And then we can look at the best subset. And what is kind of surprising here is that the best feature subset of all possible sizes doing an exhaustive search is exactly the same one we got from our sequential feature selector, the forward search, which here means that our approximation method was actually giving us the optimal results in our case, which is actually pretty cool. Okay, so then lastly, the last topic for today is to show you how we can use sequential feature selection in scikit-learn. So the mlxtend version is something I implemented many years ago, and over the years we added many bells and whistles. So there were lots of contributors to mlxtend which helped improving this implementation. But then also for scikit-learn, there was a desire to keep the function a little bit simpler. So a few years ago, we started migrating the mlxtend version to scikit-learn, and it has a simpler interface because there are not that many bells and whistles, and I would recommend you to use that one. So if you don't care about floating search, then this might be a good one to use. And also if you don't care, let's say, about a feature range, so if you are interested in a specific feature set size and you don't care about floating variants, then I would say why not using scikit-learn, because scikit-learn is very well maintained, and usually you would also reduce, let's say, the overhead of using too many libraries by just using what's already available in scikit-learn. So overall, the usage is very similar, except of course, the attribute names are a little bit different, but it also has cross-validation, parallelism, and a scoring function here to select what metric we use for evaluating the subsets. And then you can use the direction forward for forward selection and backward for backward selection. Notice here there is no floating variant. So if you want to use floating forward or floating backward selection, then I would recommend using mlxtend. And then you can also specify the number of features. And the results should be hopefully the same. And looking at this, it's 0, 6, 9, 10, and 12, which is the same that we got with exhaustive search and our manual sequential forward selection. Not the manual, but the one where we let it select the best one. Okay, so this is it then for a feature selection. So let me end this video and not keep you here for too long. And then in the upcoming weeks I'm planning to make a few more videos on feature extraction, which is a related but different topic, as you will see.